Good morning. My name is Juan Medrano. I'm speaking on behalf of my co-authors Francisco Yumbla, Seung-Yup Jung, Ik-Soo Choi, Yong-Hee Park, Eugene Oh, and Hyun-Bin Moon. We're part of the Robotics and Intelligent Systems Engineering Laboratory at Sungkyunkwan University, and I will present our paper titled Jerk Estimation for Quad Rotor based on differential flatness that was submitted to the Ubiquitous Robots 2020 conference. The content I would like to review today are our motivation for doing this research, then present the vehicle and rotor drag model that we used to develop the next topic, which is the jerk estimation model, walk you through some validation experiments, and finally talk about conclusions and future work. The motivation for doing this research is precise trajectory tracking. Currently, controllers are able to track complex trajectories with position tracking errors below 10 centimeters. However, when flying at higher speeds and as the speed increases, the control problem becomes much harder. The aerodynamic effects are more important and cannot be ignored. Previous results on jerk shows that jerk feedback is actually important for tracking complex maneuvers. Previously, the author of paper 1 showed that by computing the second derivative of the orientation expressed as a rotation matrix here, the jerk feedback term, which appears in the second derivative of A being this expression, the jerk feedback appears basically by taking the derivative 2 times of this expression, which is the velocity error. The jerk error appears. However, there is no obvious way on how to provide this jerk feedback. More recently, authors of paper 2 proved that jerk and snap feed-forward terms improve fast flight control. They compute using differential flatness, a jerk reference, which is then used to compute rate, roll, pitch, and yaw rate references that are fed to the controller, and this improves attitude and finally trajectory tracking. So we see that jerk feedback and feed-forward improves trajectory tracking. However, to the best of our knowledge, there is no obvious way to estimate jerk in quad rotors. And this is the main motivation for developing this jerk estimation framework. We used a standard widely used vehicle model in which P is the position, its derivative is the velocity, B. This model includes a thrust, which is the sum of each independent thrust generated by the rotors, and a drag force, which is modeled in the body frame and then translated to the inertial frame. R represents the orientation expressed as a rotation matrix, and omega is the angular velocity. The rotor drag model is as follows. It is composed of a constant matrix whose coefficients, a diagonal matrix whose coefficients are rotor drag coefficients, and is proportional to the velocity. The force is opposed to the direction of the velocity, and as such is modeled as a drag. Previous research has shown that the last element of the diagonal here is negligible, so we assume it is 0, and we assume that since the vehicle is symmetrical, the CRX and CRY coefficients are equal. It is possible to simplify this model to include a T-bar thrust, which now represents a augmented collective thrust, augmented by this expression, basically coming from the induced thrust produced by the motion of the vehicle, and a simplified drag term. Here, gamma is a constant proportional to the rotor drag constant and the square root of the mass times the gravity. So going forward to the development of the inertial jerk estimation model, we start with the previous expression for the translation dynamics. We take the time derivative of this expression and solve for the jerk. This step is a middle step in proving that the dynamics of this model are differentially flat. So by doing this derivation, we arrive to this expression, in which by making tau equal to the augmented thrust divided by the mass, we arrive to this expression in which all terms are either the thrust, elements of the orientation, and values that can be obtained from the inertial measurement unit, IMU. Finally, we use of the superscripts D and M to represent desired and measured values. So the estimated or measured jerk is the expression as follows. Here, all the values can be either obtained from the controller, from IMU measurements, or from estimations of the orientation. Now, if we left multiply this expression by the rotation matrix representing the orientation, we can get a model of the body jerk, in which it is not necessary an estimation of the orientation of the system. So we can either obtain an estimation of the inertial jerk or the jerk expressed in the body fixed frame. In order to verify this model, we use the flight Google simulator, which provides an IMU measurements at 200 Hz. In these experiments, we eliminated the noise and bias, since it is possible to compute those values in other algorithms, using other algorithms like visual inertial odometry. We made the drone fly in several trajectories to excite different axes of the motion, and we used this metric, which is basically the difference between the acceleration and the integration of the jerk. This should be a constant, and this metric allows us to see when the jerk estimation model degrades if this value is not a constant, which we will see in the next graphs. Starting at an average velocity of 0.6 meters and the curved trajectory, we see that the metric C, which is this green curve for all graphs, is almost constant. The velocity reached peaks near 1 meter per second. So at this velocity, the estimation is actually reasonable. Going higher in speeds, the green curve representing the offset between the acceleration and the integration of the jerk is almost constant. However, there are some peaks exactly in the moments where the angular acceleration has the same peaks. So we see the effect of the angular acceleration. Going higher in speeds at 2.5 meters per second, we see important degradation in the estimation of the jerk. And moving forward at 5.1 meters per second, we see that the estimation is degraded, and so it might not be used. Conclusions and future work. We propose a jerk estimation model based on differential flatness. This model requires IMU, thrust inputs, and orientation measurements for inertial jerk, or ignoring orientation for body fixed jerk. The performance is reasonable for speeds below 2 meters per second. In the future, we aim to evaluate this model on real flights to account for non-model dynamics and improve this model by including velocity-dependent rotor drag terms. Thank you very much.